Hello everyone, this is Vasant, a 9-pointer at IIT Bombay from the Department of Civil Engineering. In this video lecture, we are going to discuss about proof strain. So in previous lecture, we discussed about proof stress. We said that proof stress and engineering stress are almost equal in elastic region. So and we also said that in most of the engineering applications, the elements are designed for elastic region. So we can use engineering stress in that case. So that is the reason we named that stress as engineering stress. And we said that in plastic deformations, the true stress and engineering stress are has much difference. So we need to only use true stress. So that is the case of manufacturing field where we use plastic deformations generally. So now we are going to discuss about true strain. So similar to true stress, in true strain also replace the original length by instantaneous length in engineering strain. Before discussing true strain, let us take one example. There is case 1. Case 1, person, a rod L is there. First he deformed it to 3L by 2. Then after some time he deformed it to 2L. And in case 2, person deformed L to 2L in one go. Okay. So for case 1, epsilon case 1 will be is equals to 1 plus 2. What is 1? That will be 3L by 2 minus L divided by L. For epsilon 2, the reference length will be 3L by 2. The original length will be 3L by 2. Then he took the 2L, right? So 2L minus 3L by 2 divided by 3L by 2, right? So this will be half and this will be 1 by 3. We get 5 by 6, right? Epsilon case 2, in that case, the change in length is 2L minus L divided by L. So that will be 1. So if you see epsilon case 1, the value is different from epsilon case 2. If you exactly consider epsilon case 1 is less than epsilon case 2, right? So but whatever change in length is same, but in one case we did it in 2 steps, in another case we did it in 1 step, but we are getting different strains. So why? What is the mistake in this? Where we did the mistake? See, in this case we directly consider initial length of L. First it go to L plus delta L, then also we consider L, and L plus 2 delta L, then also we consider original L as the original initial length. So but in this case we consider original length this as 3L by 2 for this case, right? So there is the difference because here the original length 3L by 2 is playing the game, right? If we took this as L only, original length only, then we should have get 1, right? So the difference is 1 by 6 here, and the deformations are large. So in case of large deformations, the true strain and engineering strain has much difference. So then in that case we need to use true strain. That is the case of manufacturing field. But small deformations which happens in elastic region, the true strain and engineering strain will have almost same values. So we can take engineering strain into consideration for designing the elements in engineering field. So that is the reason we said that strain as engineering strain. Now let us know the formula for true strain. So true strain epsilon t is given by L instantaneous and changing that instantaneous length. Okay, and integration from original length L naught to final length LF. Okay, so this is the true strain, and we already said that in elastic region change in length is very small because the value of E will be large. So the theta will be nearly 90 degrees. So for large stresses, the strain will be very less in elastic region. So true strain and engineering strain are almost same. And we also said that in plastic deformation region, change in length will be more. So true stress, true strain comma engineering strain are largely significantly बोल सकता हूँ largely different. Okay. So now can we relate these engineering strain and true strain? So if we know that engineering strain which we use in engineering materials, can we get the true strain from that? Yes, of course we can get that in case of incompressible materials. Why we are using incompressible materials here? See, in engineering applications, whatever materials we use that are incompressible materials. So we can put this condition over here, right? So for incompressible materials, del V is 0, right? Change in volume is 0. So we already know that epsilon T will be is equals to integral dLi divided by Li from initial length L0 to final length Lf. So we get ln Li from L0 to Lf. So we get ln Lf divided by L. See, generally we use incompressible materials. So see, for deriving the derivation of relationship between true stress and engineering stress, we used this assumption that the material is incompressible. But in this case, if you see over here, this ln f Lf will be is equals to L naught plus delta L divided by L naught, right? So this L naught will be is equals to 1 plus delta L by L naught. So this will be change in length by Versional length, that will be engineering strain, right? So epsilon T will be is equals to ln of 1 plus E. This is true for any kind of material. Right? Because here we didn't assume that the material is incompressible. But in the case of true stress and true stress and engineering stress relationship, we assumed that the material is incompressible. So that sigma T is equals to sigma into 1 plus epsilon is for incompressible materials. Okay, so this relationship is valid everywhere, and this relationship is valid for incompressible materials. So see over here, if epsilon see if epsilon is nearly 0 for elastic region, epsilon is nearly 0 compared to 1, right? So sigma T will be almost is equals to sigma, right? Do you agree? Yes. So with this we complete today's lecture. Let us summarize before ending the lecture. We discussed that what is true stress and engineering stress, and true strain and engineering strain, and we derived some relationship between true stress and strain, and engineering stress and strain. And we said that in elastic region case, true stress and strain are almost is equal to engineering stress and engineering strain respectively, right? But in plastic deformation case, the difference is large, so we only need to consider true stress and true strain. So in manufacturing field, we generally go into plastic deformations cases. So we need to consider true stress and true strain only in that case. But in engineering applications, we generally design for elastic region. So true stress and true strain are almost is equal to engineering stress and engineering strain. So we can use engineering stress and engineering strain. So and we derived the relationship. The relationship between true stress and engineering stress is sigma T is equals to sigma into 1 plus epsilon. Here sigma epsilon are engineering stress and strain, and the relationship between true strain and engineering strain is epsilon T is equals to ln of 1 plus epsilon, where epsilon is engineering strain. With this, we end today's lecture. In next lecture, we are going to solve some crazy problems on this topic. Until then, take care. Bye bye from 9pointer.